Hey guys, I hope you are doing well. We are looking at designing an LRU cache today, right? So let's see what an LRU cache is. I hope you have already read the problem statement and went through the example, but I just wanted to list out what we need to do here, right? So we need to implement a data structure, and it should support get and put. Get reads a value for a key. Put basically puts a key and a value pair into the data structure. So what's the fuss about this problem? Why can't we just use a simple hash table, right? So we have two type of requests here, right? A get and a put, right? So if I define a hash table, I can get a value by looking up into the data structure in a hash table in order 1, and I also can put a value in my data structure in order 1. Now there's a catch in this question that there is a limited capacity of this hash table. So we need to have a boundation of the size of the table, right? Now if the size of the hash table is say 5, which means it can only store 5 keys, and if you get 6 requests, where does the 6th request go, right? So the how the cache works is whenever there is overloading of the cache, what we do is we evict or discard a particular entry in the table and make way for the new entry in the table. So for least recently used cache, our criteria least recently used means this key, any key X here in the table is the oldest key on which a get or a put has been performed. All other keys were read via one of the requests, and key X hasn't been read for a very long time. So it is the oldest such key which hasn't been read, right? So if there is a new key, it makes sense that nobody is reading X. So evict X and make way for the new key. Okay, so we know we can do get and put in order 1, right? What we can do is let's define a time variable, right? And whenever a request comes, we increment the time plus plus on a request and tag the request by this time, right? So we are time stamping our request, right? And what we do is we just put those keys in the table along with their values. We also put the timestamp on the keys, right? And whenever we want to evict from the table, we iterate over all the keys in the table, find the key with the oldest timestamp and evict it. So our algorithm still does get in order 1, but whenever we are inserting a key, right, it can happen that we need to evict something and then insert takes order 1, but eviction can actually take order of capacity, which means we need to read all the keys and their timestamps in the hash table to evict. So this is one algorithm, a naive algorithm, where we do get in order 1 and we do put in order of capacity, and this is using a time variable or time stamping the request and storing the timestamps in our hash table. So this is one way to solve the puzzle, right? But there is another way, there is a better approach where we can get put to be reduced to a order 1 time complexity. Let's discuss that. What we wanted to do was that this is a hash table and we don't want to use a time variable to maintain the recency of the usage of the keys, right? Because it's not optimal. Now we need to then maintain another auxiliary data structure which will do our time management. We need such data structure that there is a precise ordering between the elements in this data structures. This needs to be an ordered data structure, right? And what else it needs to support? So whenever we do an insert, which means a put or a get on the hash table, we need to update those time in this data structure, right? So we need to update recency for this key, right? And what else we need to do? So put can also invoke an eviction, which means we also need to be able to delete a key in this particular data structure time management, right? So these two operations need to be supported, and also put in get, we need to store those actual values. So we need to be able to get or put the key and value in the time management data structure or in the hash table. So we will focus on these two functions and see what we can do, what data structure we can use. Because get input, we can actually just put those values here in the hash table and don't worry about these. And these operations need to be in order one, right? So what's this data structure exist? So if you think about it, what we are doing is we are getting keys in increment time, right? So this is a timestamp. We're getting keys in an increasing timestamp, right? And we can just maintain such data structure that the last node actually is the oldest node and the first node is the newest node, right? So this is our time data structure. Okay, now how would we support delete a key in this data structure, right? So if we want to delete this node, we want to be able to do this in order one. So we can't use an array to do this, right? But we can use a linked list to delete the node. Now, if we delete the node, then we need to be able to link the node after it to the node previous to it, right? So we need those parent pointers as well to be able to delete the nodes, right? So this becomes like a doubly linked list, right? So this delete operation is supported in order one, and whenever we want to insert a key or update recency, we come to a node, right? We delete it and we put it back in the front of the queue, which says it is the newest. So all in all, what we do is we maintain a hash table, then each key points to a corresponding value or pointer points to a node in a doubly linked list. So this is our hash table. And what we do is now algorithm becomes if you get or a put, right? So these two things. Okay. If we get, look up in hash table, right? If it doesn't exist, return value null. Here, you'd also need to update recency, right? Which means delete this particular pointer from the hash table and insert the same pointer in front of the node. Okay. While putting, what you do is you check two things. Okay. The hash table is not up to the capacity, not full, means slot available. And here the hash table is full. Then you need to evict if slot available, put value and again update recency. And eviction here does delete last node. So we also need to maintain a pointer to a last node. Once you delete that, then you do this put value and then update the recency. Okay. So let us just, I'll show you how I have coded this, and let's just get through the code because I know this video is getting big. Another thing is, this is one such problem where you are involved with two data structure and you need to maintain two data structure to do operations, right? We have actually made another video where we discuss how we evolve to such questions, how our thinking is, and we also discuss the other forms of caches, like most frequently used cache, or a cache where you want to evict uh, the most sizable data, where you want to evict a key which takes the maximum space in your cache. Maybe you want to evict that because you want to free up your cache to get some other key, right? So we discussed those in an analogous video. You can find that video on our channel. And now let's look at the code. Okay, let's see how I have coded this algorithm. So first of all, this is my hash table, right? I store the capacity uh, in a variable to be used when I need to check how much my table is full, right? And I also declare my doubly linked list here. So this is my doubly linked list node, right? And I maintain a head and a tail pointer. So tail pointer is to do eviction, right? And the head pointer is to add new nodes on top of the doubly linked list, right? So it still maintains the data structure as such, where the head points to the newest node and the tail points to the oldest node. Okay, and all these nodes are doubly linked, so these are connected. Okay, what I do in get is update the node in doubly linked list, right? and then returns the value from the hash table. Okay, so now let's see the update node in WLAN list. So I remove that node and I add to the front. So as we discussed that, if the node is here, right, then we need to delete this node because we need to update the recency of this node. And now this node is the most recently used node, so we'll put it on top of the WLAN linked list. Right, this is what we are doing here. Okay, and then we just return the value. Right, now let's look at the put or the insert of the key value pair. If key is already there, we can do the same thing. We update the recency of the node, we update the value, right, and nothing else. Right, now if the value is not there and the capacity is full, so suppose the capacity is not full and the key is not there in the table, then what we do is we just add the new node in front of the WLAN list and be done with it. Right, now if the key is there, that means key is somewhere here, right, in the WLAN list, and the capacity is full, so all nodes are there. We need to evict the last node, this node, right? So this is what we are doing over here. So we get the tail, we get the last node, we delete it, we delete the key from the hash itself, and we remove the node from the DLL, right? And then add the new node on top of it, right? So this is the whole algorithm. You can write the remove node from DLL and add to front of DLL by yourself, but this is the crux of the LRU cache, right? Again, thanks for watching this video, guys. And as I said before, this recently used cache is one of the cache, and we have a video where we go over how to think over other eviction strategies and how the questions can be framed where you want to use a hash table and say a tree, binary search tree, and you want to store data in both these data structures, or even when you want to use a hash table and a heap, right? So those strategies we are discussing in another video called evolution of from LRU cache, and you can look at those videos. Thanks again for watching, guys. Share this video if you like this video. Please comment, and thanks for watching again. Bye.